All right. Okay. Hi everyone. So this one's on Zoom because I'm not in Irvine. I'm in Texas right now, and I'm gonna be here till May. So I think according to the schedule that I have so far, I think there should be around three or four of these that should be on Zoom, maybe five. Depends on how many we have and if like other workshop coordinators next quarter will end up presenting instead of me. Because I come back May 9th with which I think is like week 7 for everyone. So I'm planning on holding like two or three workshops after I come back. They'll be in person again. So anyway, today we're going to go over Markov chains, and this is going to be one of the building blocks for next week's lecture, which is going to be on reinforcement learning. So this is like one of the more, it's going to be a more statistical thing than it's going to be machine learning, but there's still going to be AI components to it, especially towards the end. So first we're going to go over discrete Markov chains, which are basically going to be Markov chains that have some sort of set amount of time that you can think about. It's not something that can have like decimal amounts. It's this normal way that we talk about discrete versus continuous. Markov chains in multiple time steps, which is the actual purpose of Markov chains, so that we can predict the probability that we will be someplace. Steady state behavior and equilibrium distributions, which is basically after a very long time, some Markov chains will end up having some sort of probabilities that each state takes, regardless of where you start from, regardless of which time step you're at. And then we're going to end up with MDP and MRPs, which are going to be our real lead into reinforcement learning, sort of an intro to that before we go into deeper next week. Okay, so the first thing is I have three questions for you guys. Where do you go to study? And the reason why I ask you this is because there's a couple, this is sort of a really good way to sort of start thinking about the main thing of Markov chains, which is the Markov property. So I'll ask you this. Where do you guys usually go to study?
Science library. ICS squad.
Yeah, science library, ICS squad. Not squad, quad. The other question I have is, does where you studied yesterday affect where you'll study today? For example, let's say that you went to the science library yesterday. Does that if affect where we're gonna end up studying today?
Not for me. No.
A little bit.
Yeah, like it's fair. I know for me personally, like if I usually study at the student center Starbucks. If I study at the student center Starbucks yesterday, depending on how much work I got done, I will either study there again or go somewhere else. And then the last thing is, how about the place where you studied 2 days ago? Let's say that like on Monday you studied at Langston Library. Is that gonna matter where you study today?
If it did, a lot less.
Yeah, it matters a lot less. And this is gonna be the like sort of the crux of the Markov property when it comes to Markov chains. Let me go to the next slide. Oh, let me not show that. Oh, I every time I tried to write using Canva's writing tool, it didn't work. So all my transitions are just blocks now. Let me open it up. See if this works. Okay, there we go. I'll open it up here. No need to. There. Just that one. There we go. Okay. So let's say that you're going to study today for a total of 10 hours. And these are the four places you always study here: Langston, Gateway, Science Library, or the ALP. These are the four places you study. And every hour of these 10 hours, you will be in one of these four places. So let's say you start at Langston. You can go to Langston at 10 a.m. and then at 11 a.m. you're like, I'm gonna go to Gateway. Now you're in Gateway. At 12 you're at Science Library. At 1 you're at the ALP. Maybe at 2 p.m. you're back at Gateway. Maybe at 2 p.m. and maybe at 3 p.m. you decide I really like Gateway and you stay at Gateway again. So you have these 10 hours during which there are four places that you study at. At each place, there's a probability that you'll study there again for the next hour, or some other probabilities, say I, J, and K, that you'll study at any of the other three places. These are set discrete probabilities assigned to each sequence. And my question for you is, how many sequences of places that you can study are there? Which is kind of like a very weird question, What I'm trying to ask you is that how many total sequences are there in these 10 hours? So let's say you start at Langston. Let me go back. Actually, no, let me see if it works this time. Oh no, it's not supposed to happen. And so I don't like Canva. Look at there. So let's do start at Langston. What's another place you can go to? So you're at Langston at like 10. At 11, give me another place you go to.
ALP.
Go to ALP. And then it's 12. Where do you want to go now?
Gateway.
Gateway. It's 1. Another place.
Library, that's the only other place left, right?
Yeah, go to Science Library. Go Gateway again, Langston, etc., etc. Notice that I said that at each of these times, each hour, there are 4 places you can be at. And what I'm trying to ask you is, given this idea that at each of these places there are 4 places you can be at, how many sequences of places are there? Like, how many total sequences can I make out of this?
4 to the 10th power.
Yeah, 4 to the 10th power, exactly. Let me go back to here. This is going to be m to the n. There are m places you can study at, and you're going there for n discrete hours, which is the 10. So if I were to model this, that would mean that I have a huge table of probabilities that there's 4 to the 10th different sequences that can happen. There are 4 to the 10th probabilities that I need to know if I want to predict where I'm going to study each day. If on Saturday I'm still studying for 10 hours, I have 4 to the 10th probabilities that I need to assign to all these sequences. Isn't that kind of crazy? That's a lot, right? That's where the idea of Markov chains come in. That you have these M states that can take place, and each of these M states depends, like your next state that you will go to depends only on your current state. So rather than thinking about, let's say you had 4 to the 10th different sequences, right? That's a total of the sequence on one day has a length of 10. Because there's 10 hours, 10 places you're going to go to. If I told you that the only way that it matters where you'll go to next is just your current, and then that is the only way you're going to know where you're going to go next. What you did before that does not matter. And that decreases the probabilities that you care about by a lot, right? That's what the idea here is. That if I'm have 2 places I'm going to, Langston and Science Library, the only probabilities I need to know are the ones if I'm staying at Langston and if I'm just going to go to Science Library. It doesn't matter the probability that I was at Langston 2 hours ago. It doesn't matter the probability that my previous sequence was Langston, Science. It only matters what my previous one was if I'm kind of thinking about where I'm going to go now. So these different places here that we have, like Langston and Science, these are our states. These are sort of the places we can be, the situations we can be in. That's how to think about states. And xt is your state at a given time t. So if I told you, hey, we're starting at Langston, then x0 equals Langston. x1, let's say I tell you, now we're going to go to Science Library. x1 would be science. That's like one of the main vocabularies we're going to use a lot. And oftentimes what we'll have is that these won't be named letters. They'll be named something like a number, like 0 or 1. So if x0 equals 0, we're at Langston. And if x1 equals 1, for example, then we're at science. This graph here, this representation, is called a directed graph. And it's a way to represent movement between states. The directed is because these arrows have a direction to them. So it's not like just a straight line, no direction. There's a specific way that you're moving through this graph. The way that I would visualize is that it's like you're walking. You're walking from Langston to science. You're walking or inside a Langston, just staying there. That's sort of how to think about this graph. And of course, this here, the Markov assumption, this is the main thing that we care about. And this is what everything is based on. This is what a lot of reinforcement learning is based on too. That your next state depends only on your current state. What you're gonna do tomorrow, where you're gonna study tomorrow, depends on where you studied today, not where you studied yesterday or 2 days ago. Which is what you guys were saying too. If you're studying at the science library today, then maybe tomorrow you'll study the science library again tomorrow because you really like it there. But if you studied at Langston 2 days ago, that's not going to affect where you're studying tomorrow. You go to another state or stay at that state based on some probability P or K, whatever that is. And that's what this probability here. Notice something. We're going to talk about this again too. That the probability that you go to these different states, it adds up to 1. The probability that you stay here or you leave, it adds up to 1. And then the last thing to talk about is M is what we're going to say the number of states. So let's say that this is the states that we're going to go to. What is M equal to? Pretend you can't see the answer right there.
M equals 4. Or I guess in this particular diagram, it's 2. There's only
Yeah, M equals 2 because there's only 2 states. We can either be at length or be at size. That's it. Any questions so far about the vocabulary and how to describe things now?
So essentially, this is like choosing what restaurant you're gonna go eat at for dinner. Like, it doesn't really matter what restaurant you go to tomorrow, unless it's the same one you went to today, in which case, like, you're just gonna be eating the same thing you ate yesterday, so you don't want to, so the probability changes.
Pretty much, or the probabilities are set. So if you're thinking about like the restaurant idea, you could say that if I went to, I don't know, an Italian cuisine and I'm and like another option, another cuisine, like I like Thai food. The probability that I do Italian to Thai will be 1 because you said you don't want to eat the same food in a row, right? Because the probability you're gonna have Italian tomorrow if you had it today is 0 because you don't want to eat the same food 2 days in a row. So that would be like a graph like this where it's just cyclic. You're gonna go to Italian and Thai food every single time.
Makes sense.
Let's erase that. Actually, I don't need to erase it. It's not gonna carry over like a whiteboard. So let's say that you started at Langston. Where can you go from Langston to science if, say, we're just going infinitely? Like, first, let's start small. Let's say that we just want to study for 2 hours. X0 is Langston. What summer we can go after this? If we're studying for, say this, we're studying for 2 hours. So our time steps are x0 and x1. We know x0 equals Langston. What can x1 equal to?
X naught could be science or Langston, P.8 for science, P.2 for Langston.
Yeah. If we're starting at Langston, we have 2 places we can be. We can either stay at Langston or go to science. How about if we started at science? What can x1 be?
Science or Langston.
Yeah, exactly. It can be science or Langston. And so I'm just trying to give you guys like an idea of what these sequences are like. And then again, it's the same thing here. We're back at Langston. We have 2 places we can go. We can go to Langston again, or we can go to science. Same thing here. It's the same exact idea here. And that's just sort of the idea of how these chains are created. It's these long sequences where the next one depends. It's conditionally related to where you are right now. So a way to represent this is the state transition matrix. The state transition matrix, as scary as that sounds, is literally just a matrix of probabilities of the probability that you'll transition from one state to another. You'll transition from state I to state J. So in this case, we're going from Langston to Langston, science to Langston, Langston to science, or science to science. That's just how it works. So you have 2 states. The probability that we do Langston to Langston is this one right here. Langston to science is this one right here. Science to Langston goes this way, 0.2, and science to science is 0.8. So this shows the transition over one transition period. Let's say that this is where we're going to study every day. This is showing where we're going to go from Saturday to Sunday, for example. This is not just Saturday because you know where you're going to go tomorrow with this probability. The probability of 0.6 is the probability that you're going to be studying at Langston today, and that means you're going to be studying at Langston tomorrow. Each row here is the initial state, and each column is the terminal state. So when I say IJ, I'm saying that we're going from I to J. The row here, so let's say this is 0, 1, 0, 1. So P 0, 0 is going from the zeroed state, links in, to the zeroed state again, links in. I to J. Does that vocabulary make sense? Remember, I can't see you guys. If you're nodding, I can't see that. You don't have to say yes.
I am nodding.
Okay. Now, if you notice on the same thing I mentioned earlier, is that these rows, they add up to 1. This adds up to 1. This adds up to 1. And that brings us to this very important formula, this summation, that the probability that you go from links in plus links into science, or I don't know, links into gateway, links into the ALP, links into ICS, that will always add up to 1. It'll always add up to 1. And this equation here, this is going to be very key. And this makes sense, even though it looks a little like, oh, why are we doing probabilities? It makes sense because when we say the Markov property, where I go next depends only on where I am now. That's conditionally related. Where I go next depends. It's based on the given of where I am now. Does that make sense?
Indeed.
Okay. So that's like a very that's what like the most important thing about this is. This is like the equation about it. Now the next thing we're talking about is the Markov property, a little bit more in depth, and independence. Now even though this sounds weird, states at different times are not independent. The reason why I say that is that let's say you were at Langston at 10 a.m. and you will be at Langston at 12 p.m. What is the probability that happens? You might be like, oh, let's go to the previous name, zero point 0.6. It's not zero point 0.6. Because think about it. It depends on where you were at that middle time. If at x0 links in, x2 also links in, the probability that this happens depends on where you were at x1. If you were if you were still at Langston at x1, your probability will be at Langston again at x2 is zero point 0.6. If you were at science, the probability changes. It's zero point 0.2 now. States at different times are not independent. There is a relationship, and they're conditionally dependent on this middle time here. However, if you condition on the current state where you are, if I said, where will I be at x2 given I'm at x1 Langston, then the past and future are independent. Does that make sense?
Yep. Nodding verbally.
So, and this is the main thing about the Markov property. If this was not true, that states at different times were independent, then your Markov property doesn't quite hold the same, because then it means that all of your past is independent, all of your future is independent, and it doesn't really matter anymore. You'll that means there's no prediction involved. You're just at the same state forever, right? Or probably are just one. Like it's cyclic. You know that you'll always be at science on like even numbers or something like that. But this is like sort of one of the main. This is sort of just to really drill in the Markov property and the idea of independence with this. Now we're going to try drawing our own directed graph. So there's two states you can be in. You're either rotting on your phone or you're locked in. Now, you can be rotting and you can just stay rotting. So if you're in the rotting state, you can stay rotting. Same with being locked in. You can be locked in and you can stay locked in. However, you can also go from rotting to locked in with the probability of P. You can also go locked into rotting with the probability of K. Now we're going to make this directed graph. So first thing we want to do is draw out our states. How many states do we have?
2.
We have two. Okay, let's draw two circles. And what are our two states?
Locked and rotted.
Okay, so we'll say this is 0 for rotting and 1 for locked in. I'll say it in parentheses. Now we'll skip this one. We'll go here first because there's actual probabilities attached to them. We can go from rotting to locked in with the probability of P. So what should our arrow go? And what should it be labeled?
Uh, arrow from rot pointing at locked, labeled P, and then opposite labeled K. And I assume that there will also be an arrow from 0 going back to itself, labeled 1 minus P, and then the same thing with 1, just 1 minus K.
Yeah, exactly. That's exactly right. It'll be just like this. So the reason why it's 1 minus P and 1 minus K is because of what we talked about here, where if you have the probability of everything that's I like to think about everything involved with rotting will add up to 1. That's like the main idea here. And so this is what a directed graph is. Now we'll look at the state transition matrix. I don't think we have enough space. No, we can have space. Let's see if I can I move this? Oh, I can. Nice. Now let's make our state transition matrix. So remember, it's I to j. So we'll do 0, 1, 0, and 1. So remember, this will be the probability we go from 0 to 0. It's I to j. I to j. Remember that. What's the probability we go from 0 to 0?
Uh, 1 minus P.
Mm-hmm.
And
How about 0 to 1?
P, and then 1 minus, or then K, and then 1 minus K. So you got the 1 minus.
Yes. Yeah, because from 1 to 0, which is k, and then just from 1 to 1, which is 1 minus k. And that's exactly right. That's the same thing that we got as well. So now I have another question for you. Let's say that if you rot for 4 days, then you have to lock in. No excuses. Doesn't matter what happened. 4 days straight locking, 4 days straight rotting means you must lock in. But we only have 2 states. So how do we model this? Do you guys have ideas? A hint is it'll involve more than just our 2 states.
Well, we're gonna need to, rot for 4 days, number one. I guess we'll need
But
to model multiple sets of that little diagram there. You'll have to have multiple of them stacked next to each other. And then if you take the path where you go 0 to 0 to 0 to 0, if I said 0 4 times there, then the next day, the only path left to walk through that graph is going to be to the one that says 1. So we're going to need to add extra nodes here.
like that?
Yeah, like that.
Yeah, that's right. So basically, remember how earlier we had a probability that we just went to ourselves at 1 minus p? If we're saying that 4 straight days, that means that when we have the probability of rotting again at 1 minus p, then we need to have like some sort of counter. We need to go to like another state that tells us that which day of rotting we're on. So the probability of, let's say, 1 minus p, now we're rotting again, another day of rotting. Now there's probably 1 minus p, we go here, but remember, there's a probability that we can go from rotting to locked in as well. So there's still a probability that we can make a comeback and still go back with p. Same thing here, we can still go back here with p. This is going to get very messy very quickly. Same thing here too. But what about here? This is an important state. This is the last day of rotting. If it's the last day of rotting, we have to lock in. So there's no next state where there's no probability 1 minus p that we can return back to this state over here and rot once again. We must be locked in. So what happens to this probability here?
One.
Exactly, it's 1. It'll be 1 because we have to lock in now. Now we're back here. And now we can do that same cycle again if you would like. Does that make sense to everyone?
Yep. Yes.
Yes? Okay, let's go on. So that's exactly, oh, I don't know why this got cut off. It's supposed to be connected. Same thing with this. Oh, you guys already saw. I don't know what happened when I downloaded this from Canva. That was weird. Okay, but how do we know the probability we will go from rotting to locked in after we've rotted for a couple of days? So let's say that I started off rotting and I want to know what the probability that I will be locked in after 5 days. How would we know that, right? We would have to think, oh, I could just, it could have been like a sequence of probabilities where I just went 0, 1, 0, 1, 0, 1, and I could have ended up locked in here. Or maybe I ended up, okay, or I could have ended up just being completely just rotting here, and then I came back and locked in. Or I don't know, so many things could happen. You don't know what will happen on the fifth day. That's why we're going to talk about multiple time steps. The probability, which comes back to this equation that we talked about earlier. The probability that I will be unlocked in on Friday depends on all those middle probabilities. Remember we talked about the Markov property independence, and we said that if I want to know if I'm studying somewhere on the second day, it depends on where I am the day before that. Right? This is the same thing we're going to do, and it's just going to be a really big equation. That's pretty much it. So if I'm saying that at x0 I'm rotting, I'm here, and after some mysterious things I could have been here. So what I could have done, I could have been here. But for sure, no matter what I did on that first day, I ended up, wait, my mistake. We started off locked in. Let's see here. We started off here. No matter what happened on that middle day, whether it was, I could have been here, still locked in. I could have already been rotting. I ended up here. This was my destination. Why is this in highlighter mode? That's what happened. So with this equation, the probability that I'll be locked in on Friday if I'm rotting today means that I need to account for all of those middle probabilities, all those middle states that could have been on X1. The fact that on X1, I could have been locked in again, or I could have been rotting again, and the associated probabilities of that. Does that make sense? The way we're going to think about this is just going to be like decomposing this conditional into like two baby conditionals, if that makes sense. Because remember I said that what matters is where we were on X1. The two places we could be on X1 are 1 and 0. So we know for sure that we're here. What matters is where we were here. The reason why we're writing it like this is because we're gonna be locked in on what's today's on Friday. We're gonna be locked in on Friday. We know that for sure. We're gonna be locked in on Friday. We know this. We are currently rotting. We know that. We know that. What we don't know is where we're gonna be here. So the two sequences that we can have are rotting, locked in, or locked in, locked in. So what this is just saying is what's the probability that we're locked in on Friday and I don't know, locked in on Thursday, given that we're voting right now. So this would be one here, and it'd be zero here. Because that's like the two states that we can be in on Thursday. And that, because Thursday will determine, we have two different probabilities of what will happen. If we are here on Thursday, then the probability that we're going to be locked in tomorrow is 1 minus k. Versus if we are here on Thursday, the probability we will be locked in on Friday is p. It's two different numbers. That's what we have to do this. Does this equation make sense to everyone? Yes? Okay. Let me erase these check marks so it's space. But I was thinking, wait, these have ands. How are we gonna deal with that? Well, how are we gonna know what these probabilities are? Remember what I said here? Oh, oops. I meant to erase that part. If you condition on the current state, the past and future are independent. Who remembers that if you have an and, probability A and B, and A and B are independent, what is P A and B equal to?
A times B.
Yeah, it's probability A times B. So we can apply that same root of very simple elementary concept to this here, where we can take this equation here. I'm gonna use a different color. This will be blue. This will be green. I also like that I have two colors now. Didn't have that with the whiteboard. With the Markov property, the past and present are independent if conditioned on the present state. So now we can say, for the first equation, probability x2 equals 1, given that x1 equals 1, right, we have here, times the probability x1 equals 1, given x0 equals 0. This is our sequence. This is our 0, I'll say 0, 1, 1 sequence. That's this right here. Our second sequence is going to be 0, 0, 1. So that's this right here. And if you look at it, like really digest it, it makes sense. You're going like that. Does that make sense? How we got there?
Yes.
Okay, so now let's do the next one. So you guys tell me, what is this probability going to be?
X2 equals 1, given that x1 equals 0. And then times the probability that x1 equals 0, given that x0 is equal to 0.
Yeah, exactly. So now we can break this down further. What is the probability that x2, what is this probability going to be equal to? x2 equals 1 given x1 equals 1. What is that going to be equal to? This is the probability that given that we're locked in, we're going to be locked in.
1 minus k.
Yeah, it's 1 minus k, exactly. What about this one? The probability x1 equals 1 given x0 equals 0.
K.
Yeah, because this is the probability that wait, no, it's not k. This is the probability that we're at 0 and we're gonna go to 1.
Oh, it's going to be p.
Yeah, it's 0. I know it's a little weird to look at, but it's given that we're at 0, that will be at 1. So it's p. Well, what about this green one? What's this probability here going to be? So a way to think about it is that this part here, use yellow. This is I, and this is J. So if you look at this table, this is I and this is J in the transition matrix, you can quickly go, okay, what is my matrix value where my row is 0 and my column is 1? Where is 0, 1? What does that equal to?
Probably x2 0. Would that also be just p?
Yeah, that would be P right there. It would be P times. And then what about this probability here?
1 minus p.
1 minus P. I'm going to solve that out. Actually, we don't really need to. Let's leave it like that. But that's a probability that if you're rotting today, then on Friday you'll be locked in. It's the probability there. So if let's say we assign them numbers, you can solve that out. Yeah, that's correct. Well, I guess I had a typo there. That shouldn't be K, that should be P right there. It's my bad. But yeah, that is the idea of multiple time steps. And if you, from doing this problem here that we did, you might notice something. When we had this 2 to 0, we sort of downsized. We looked at, okay, what's 2 to 1? What's 1 to 0? We were breaking this larger problem of 2 to 0 down to smaller pieces of what's 1 to 2, 0 to 1. What does this breaking down remind you guys of in computer science?
Dynamic programming.
It's dynamic programming. It's also recursion because you're sort of working backwards. You want to know what like the I don't know if it's, let's say, the Fibonacci sequence thing. What's like the number at like 5? Like you have to work backwards, I think.
Yeah, because it depends on the two previous numbers before it.
Yeah, the probability that what you'll be doing at time step 5 depends on what you were doing at time step 4. You have to go backwards. It's recursive. So that's what this this equation is talking about with multiple time steps. That to do a two-step path to time step 2, we took a one-step path from t equals 1 to t equals 2. We took a one-step path from t equals 0 to t equals 1. So if I want to take a n-step path to t equals n, I have to take a n minus 1 step path to the time n minus 1 at some random state m. And then I have to take a n minus 2 step path to the time n minus 2 at some state k to get to state m. This is like what the recursive idea comes from, and that's where this equation comes from. And even though it looks kind of scary, in practice it is not. Um, Typically no one's gonna ask you to solve this out. This is just so I want to make sure like it's when you do machine learning in real life, you're not gonna have to solve this out by hand. I just want to make sure everyone has a good basis before we get into more complicated things like MDPs. This is just saying that the probability of you being at time step n, given that you're at some other spot at I, depends on the state before that, at that time before that, given that whatever that other one before that is, etc., etc. And then you start from time step 0, account for every single state, multiply by that probability of getting to that state, and you go on from there. The main thing is, as long as you understood how we did this, why isn't this working now? As long as you understood how we did this, it's all good. This is just like just a thing to add. This is what really matters. State vectors. So what state vectors are, as scary as this seems, is just some time, what are the probabilities attached to that time that you're gonna be at some other state? So this is saying at time step 0, Is somebody saying something?
No, I think it's people outside.
Okay, okay. Um, so basically what this is saying is that at some time t and at some initial state, what is the probability that I will be at all the possible states I can go to? So for example, at time step 0, if I'm starting at Langston, the probability that of all the states I can go to, which is Langston and science, probability I can go to Langston is 0.6, probability I can go to science is 0.4. I'm gonna switch colors because it's very hard to see. So now you're wondering, okay, that makes sense to me. But what about at time step 1? If you look at the previous equation, or if you just think about it, the probability that at time step 1 you're going to be at some state j, it depends on the probability of where you were before times it's the probability of the state that you're going to go to. So whatever that current probability is, let's say I'm going from time step 1, I want to go to, I don't know, science. You have pi 1 science. It's the summation of all the initial states you can be at to science times the probability of all of those initial state vectors. So it's saying that if I want to go to science, then this summation will be equal to the probability that links in science times 0 links in plus probability of science times the state vector of science. And if you think about it, it makes sense because when we talk about things like the Markov property have independence plays into this, you got to multiply them. But that's the way that that's the way that we predict. And that's how we get the new state vector. And so if you don't care about where your initial state is, the probability of just all the states you can be at, like that entire matrix at another time, is just the transpose of this matrix times the initial state row vector that you had at like the previous time step. When we do a practice problem of this, it'll make significantly more sense. So all this is saying is that if I am currently at time step 0 with these probabilities, my probabilities at time step 1 will just be that old probability, the original time step 0 probability, times my previous probabilities. So if I'm at time step 1, this is my matrix T here, and this is my previous one, T of n minus 1, or 1 minus 1, I guess. And so at T2, my probability will be whatever this thing here, this multiplication will become. So whatever the T1 is times T. That's like the formula. And at time step 3, it'll be whatever was at 2 times T. And it's because this makes sense. Markov property, everything depends on your previous state. Your state transition matrices, new probabilities depend on your old probability. And so if you keep following this along and you keep going down this path, the time step at n is going to be equal to, because T2 is equal to T1 times T. T1 is equal to T times T. It's T to the n transposed. Well, T to the n times T. So all we care about is the state transition matrix itself. That's what the probabilities will become. Does that make sense? Does that make sense to everyone, how this formula works?
Yes.
Okay. Who remembers how to do matrix multiplication?
Partially.
A little bit? That's okay, okay. We're gonna do this together. We're gonna multiply these two out to figure out what it's the only matrix multiplication we're gonna do here. That's it. So at T1 is just going to be these multiplied together, 0.6. So there'll be this one times that one. So it'll be this one times that one. 0.6 on 0.6, oops, plus 0.4 times 0.2, right? And then we're going to go on to the next one, which is going to be this one here. So 0.2 times 0.6 plus 0.8 times 0.2. And then same thing here. 0.4 times 0.6 plus 0.4 times 0.8. And then here's going to be 0.8 times, what was it? 0.8 times 0.8 plus 0.8 times 0.4. And now we're not going to solve this out because the answer is on the next slide. That's what they become. You're like, oh wait, this is interesting. You know, the probabilities. Some of them went down by a lot. Some of them, they all changed. But the main thing I just want you guys to see here is that as you increase your time steps, you'll notice something funny happen to the probabilities. They get closer and closer to some mystery value. After 10 time steps, the probabilities, like even from 3 to 10, they're getting closer and closer to the values of like 0.33 and 0.66. So what do you guys think happens as time approaches infinity for this state transition matrix?
It'll kind of start settling around 0.33 repeating and 0.66 repeating.
Yeah, it'll settle around like 1/3 and 2/3. And that brings us to the idea of the steady state distribution. And steady state probabilities of a Markov chain are the probabilities of the system being in a specific state. This does not happen to all Markov chains. It only happens to a certain kind. I forget which certain kind it is, but I think it's like ones that don't have like absorbing states or something like that. Like you can't like go to one state and then you stay there forever with the probability of one. Those are the only ones that don't have steady state distributions. But the idea of a steady state probability is that as time goes to infinity, you'll end up knowing that like these probabilities that you'll just be at this state gets fixed. So in this case, the probability that you're at Lincoln will be 1/3. The probability you are at the science library will be 1/6. I mean 2/3, for sure. And so this is the same exact thing, same formulas as before. The only difference is in order to solve and know what these steady state probabilities are, we are going to be doing system of equations. And we're going to be doing that in the next slide. But first, let's talk about this over here. So what this is basically saying is that the probability that you are at some state, every probability that is again going into that state. Remember that every probability going into that state is going to be equal to 1. Does that make sense? All the probabilities going into the state will be 1. So like, for example, the probability that and I'm blanking, the probability that you're going to be going from 0 to 0 is 3/5. The probability that you're going to go to 0 is from science to Langston is going to be 1/5. So those probabilities, just like we saw before, that like remember we talked about the summation. I'll just write it out. Why am I scrolling? We said that the probability. Oops, that's wrong. That's the same thing that applies over here. It's the same exact thing. But the key thing here is this over here, that the probabilities of like in each state transition matrix, the original T0, the given state transition matrix times the steady state row vector is going to be equal to that steady state probability. In this example, it'll make a lot more sense. Like I'm not explaining that clearly, but you'll see what I mean. So the steady state probability that we're going to be at Langston is going to be equal to the probability that we go Langston to Langston, which is 3/5, is here, times pi 0, 0, times pi 0, 0, times pi 0, because we're talking about here, we're going from Langston to Langston. So pi 0 ij, and our j can be 0 or 1. So first we're doing 0, 0, then we'll do pi 0, p0, 1, which is links into science. So that's this value over here. So we'll write these out. So that's here. Now, the other thing you can do if you're in LinkedIn is go to science library. And I mean, another way you can get to LinkedIn is through the science library. So you can go science library to LinkedIn. And this is a probability of 1/5. So when we're talking about steady state probabilities, remember, this is just a probability you are in that state. So the reason why it's that the probability of being at Langston is equal to 3/5 plus 1/5, so to say, is because the probability that you're going to be in Langston is through two routes. You're in Langston staying at Langston, or you're from science going to Langston. That's why we set it up this way. And the reason why we have pi 0 and pi 1 here is because these probabilities are dependent on where you were previously. Same idea again. The probability that you're going to be at Langston is dependent on where you were before that. Markov property again. So we can set up the same thing for pi 1. Just erase that thing.
What does the different pi's mean again?
Those are the state row vectors. So it's basically it is a steady state row vector, which basically just means that let me reword this. Pi is a row vector. So this. Pi 0 is the probability that if you're at Langston, the probabilities of all the next states you can go to. So 0.6 if you're going to go to Langston again, 0.4 if you're going to go to Science Library again. Pi with this little dot on top is the steady state probability. That is one number. That is the probability that you're at that state. So pi with a little dot and 0 is the probability you're at Langston. It doesn't matter what time it is. None of that matters. Just a probability that you're at Langston. Does the difference make sense between pi and pi with the dot?
Yeah, so pi with the down on the top means what's the steady state probability you're just at this specific spot. Pi with just the 0 is all the different ways or all the different states you can get to when you're at Langston. And then pi with bottom 0 and top 0 is like, given that you're in Langston, what's the probability that you go back to Langston?
This is just a number that no matter what time it is, no matter what, the probability that you're in Langston doesn't matter what time it is, doesn't matter about anything. Just the probability that you're in Langston. Because eventually this here will reach a steady state and the probabilities will become fixed.
How is it different from pi just to the dot on top?
It's the same thing. So just pi with the dot on top, this is just like, so let me do like this. Let me erase this too. This is just a steady state row vector. This is just a steady state probability. When you add subscripts, it's saying that, okay, this is at a specific place that I'm at. So if I had 0 here or 0 here, this is the Langston's row vector. This is Langston's steady state probability. But just as is, it's just steady state probability and state row vector.
Okay.
So if you want to solve for what the steady state probability is, This means that it's a probability we're at this place no matter where we came from. So we have to account for all the places that we can come from, which is Langston or just science. So the same thing we have to do for science library as well. So how can we get to the science library?
You can get to it either from itself or from Langston.
Yeah, so if we're going from itself, what is that probability that we're at science, we're staying at science? Wait, that's 4/5. And that probability is us coming from Langston. So it's going to be 4/5 pi 1. And then the other one is that if we're going from Langston to science. So that's 0.4, which is 2/5. So now we have these two equations, but still there's one part that's missing. And that's this. The probability of these two added together will be 1. And you remember that from right over here. And it's the same thing that's always been there, like the summation of Pij, that's always what's going to be a given. And it's the same thing that's over here too. The steady state probabilities will always add up to 1. So given these systems of equations, let's solve it and figure out what the steady state probabilities are. Okay. So first, let's move this to the other side. That means we have F5. Then we have this. You can plug that into here. Which means pi 1 equals 2/3. Does that make sense? And it aligns with our results here. Do you have questions?
No.
Okay. This is just the same thing. This is just the answer. Now we're gonna get into less mathy, more. One second, this should be connected here. Direction was connected. I'm gonna double check. Wait. I don't know why it's like that. Okay. Now we're gonna talk about Markov decision processes. So an MDP is the same thing as a Markov chain, but it's gonna be slightly different. The reason why it's different is because at each state you're making a decision attached to some probability, but now it's like you can do something called attaching rewards to it, and when you add rewards, it becomes a Markov reward process, which brings us to reinforcement learning. So the other thing is, in this case of a MDP, it's the same exact stuff as a Markov chain, but now you have a goal. There is a specific state that you want to get to. So in this case, I want to pass the class. This here is my goal state. This is my goal. This is where I want to be. And I can start from anywhere. I can follow any path I want, but that's where I want to get to. So I want to pass this class. What decisions should I make? Give me some sequences that'll make me end up at pass the class.
Assuming we're starting from right, you can go to class, then go to the discussion, then you can day drink, and then you can go back to class, then you can go to your discussion, and then you can back to class.
Yeah, You can, I'll just highlight it, like that's easier. Can rot, go to class, day drink, and then what did you say? We can go to class, discussion, then pass. What's another sequence?
You could rot for 10 times in a row and then day drink and then pass the class.
That's true, you can also do that.
That's
That's another option.
Yeah, pass and like,
that's a lot.
what else? What else could we do?
And then, yeah, he take drink pass. Go to this.
Technically, you can also just go day drink to pass. That is also a valid thing to do. You can just go straight from here to here.
Mhm.
But yeah, there's a lot of different decisions that you can make to get to this end goal state. Now, a Markov reward process now is gonna get a little different. I don't know why this arrow got like deleted when I downloaded this. A Markov reward process is the same as a Markov decision process, but now there are rewards attached to each action you make. For example, if what we care about is passing, but all we want to do is rot and day drink, we can attach large rewards to the action. Oh, not this action. No, we don't want to do that action. We can attach a large reward to something like rotting. We can say, hey, rotting should have a reward of like 10. Rotting to day drinking should have a reward of like 5. Going to class, rotting to going to class should have a negative reward because that is not what we want to do. And drinking to passing the class or passing the class should have like a reward of 10. So each state has a reward attached to it. That's the idea. That you want to have certain states be where you want to be. So obviously your goal state should have the highest reward because that's where you want to be eventually. But all these middle states are the ones that you can adjust things for. So this is an example of that. Don't know why it's got deleted again. It's the same thing as a Markov process, where S is the set of our states, just like X was. P is our transition matrix, just like T was. But now we have R, which is the reward function. Remember how we said that probability that I'll be at Lincoln, given that I'm at science, is like 0.6? Now we can have a reward. The reward, this E means the average. So the reward is, let's say the average reward that given that there's the reward 1 if you're at the running state. What is like the average? What is the average reward that I get if I'm rotting? What is the average reward I get if I'm going to class? Average reward I get if I am going to discussion. That is a new thing that we're going to add to Markov reward processes. That now there are like tangible things added to the decisions that you make. Does this concept make sense?
So it's like, what are the different rewards you can get from this specific state? Like,
Yeah. So this will make more sense now over here. What are the different rewards attached to different sequences? That's like the main thing that's here. Because now the different sequences I take have different meanings now. The different sequences aren't all like equal. Different sequences I take will benefit me or harm me in terms of the amount of reward I get. So if all we care about is rotting, drinking, and passing, what has the highest reward? What sequence?
rot infinitely.
If you rot infinitely, then you'll have infinite rotting, but then you're never gonna pass the class.
Well, what
So that
about,
is true though. That is true. Rotting infinitely, that's what I'll put over here.
Because you'd want to rot the most you can and then only do day drink and pass the class at the end. Because once you get to day drink, the only other option you have that doesn't hurt you is pass the class.
That is true, that's true. And we'll talk about that idea in the next slide. If you rot infinitely and then at the end you go, I'm a drink. Oh bro, why is Siri on?
Siri wants to drink too.
yeah,
Drink, then me too.
So let's say we rot infinitely, and then at the very last second we drink and pass, we will have a crazy reward. Right? What's another sequence we can do?
Assuming for some reason that our reinforcement model here doesn't want to be as brain rotted as it can possibly be, which I don't know why you'd ever want to do that. You can go rot to you can go rot to day drink to go to class, go to discussion to day drink, and because you can do a cycle of class, discussion, day drink, because if you from class discussion, you're only losing 3 points, but if you day drink, you're gaining 4 points. So you can actually do the same thing almost as if you were just rotting infinitely. You can go to class and discussion, and you'll get the same reward as long as you make sure to do a lot of day drinking. You'll get the same reward, and then you can just go straight to class right again.
That is true. That is true. Yeah, that's another thing we can rot, and then we can just keep, class discussion, drink, and at the last second we can decide we're gonna pass the class now. Yeah, that is another option we can do. What else? Let's try to get like 3 good ones.
Just imagine just sitting in class the whole quarter, and then the very final they day drink and then go to the final and pass the class.
Just like waltzing right up fast or like tripping over themselves.
They're falling. They have the beer in their hand.
They literally have you can see the tip of like a Jack Daniel's bottle poking out of their hat.
Exactly.
This is my final. This is my final. 100%. 100% is the final immediately passes.
Just flawlesses.
Yeah, that's the ideal case for this MRP. That would be like the ideal case. Get the most reward doing that. But yeah, that's that sums up a lot of the MRPs. Now, this idea that you guys have about I'll just go in this sequence and stay there infinitely. It's good, but there is one thing that we add to models called the discount factor. First, I'm talking about everything, then we'll talk about that. So we have, this is very simple. We're going past this, but let's say we have rotting and locked in as our states. And we want to do well. We want to lock in. We want to do well on our exams. You have these 2 states, and our actions could be like putting the phone away and studying, or picking up your phone and rotting. Those are the 2 things you can do. Our transition model is just our probability distribution. That's just T that we talked about earlier. We can attach rewards to things. We can say the reward is positive if you study and negative if you rot. And if you get a certain amount of reward, then you pass the class. Otherwise, you don't. But you don't want to study. You want to rot. So we want to rot as much as you can, but still get the amount of reward that's necessary to pass the class. Now, that whole thing I just said, that's what the policy is here. Policy is that if I'm rotting, immediately go study. That could be a policy. It's how you make the decision, how your model makes the decision. This is the main thing of reinforcement learning. All those little AIs that play Pong and whatnot, they all have some policy, some rule, or in AI cases, sort of like the algorithm that they developed that maximizes its profit, maximizes its reward. That's what you want to do about with the policy. The return is the total reward after some time t. Now, note that I said discounted reward. The discount factor is, what do you care about? Do you care about a reward after a long time, or do you want to get your reward immediately? So if you go back to our example here, let's see. If I said that our reward that we care about is a long reward, it's a reward after a long time, these are great options that we've got. But if I said that I want a reward now, what's the fastest way I can get a reward, then your answer could be something like rot, drink, pass. Because that would be 15 as your reward. If I say that what the discount does is it takes your reward and multiplies it by some discount value, let's say 50%, to the power of the number of how long has it been? So if you're saying that, like, let's say I do infinite rotting, as time goes on, my reward of one is gonna get smaller and smaller. First I'll reward of one, but after I'll have a reward of one, and then as I have a 50% discount rate, after one time step it gets halved. After two time steps, now you're getting even less, and as the time goes on, you're gonna have a very, very small amount of reward. Now, a discount factor closer to zero means I want something closer, because if you have a very big discount factor, you're going to be decreasing the reward quickly, and that means you want to get rewards fast. Now, something closer to one, that means I just want the same reward. Let's say my reward was literally just one. I don't want to do like some no 99% math stuff. Was just one. Then it doesn't really matter. Then I can do things infinitely, or if I have a 99% discount factor, it'll very small decremented by only very little. So these two options would be great. So that's what the idea of discount factor is. Is that what do you care about? Are you saying like is my final exam next week and I really need to lock in, and that so I really want to get my reward of just 15 very fast, or do I have like a month or so I can keep drinking as much as I want and I will still do fine in the class? That's what the idea is. And these are like the basis of a lot of reinforcement learning. Every RL problem can be boiled down to a MRP. Does this vocabulary make sense to everyone?
How does the discount factor, like in say our example, you said like it would choose one path over the other. How would it like example, like say it's closer to one, so it's more far-sighted, so that means that it's prioritizing more rewards over long run, but what would that look like in this specific example if it works?
So if we have a discount factor that's closer to one, then what we care about is, say, rotting infinitely. Rotting infinitely will be fine then, because we're not losing much of the reward then. The whole point of a MRP is I want the biggest reward value. So let's say I have 3 days, I have, I don't know, 4 days to, 4 days is short sighted. Say I have like 15 days to study, 15 days, and every day I do one of these things. And if I rot and my MRP or my discount value is very close to one, then I'm not going to lose much of this one reward, right? My total reward will be about 15, maybe a little bit less than 15, maybe like 14.8 or something like that, but it'll be close to 15 because you're not taking away, you're not discounting much of this one. If that makes sense. That's what the idea of the discount factor, that I'll keep doing this. The model wants the largest reward. It wants to have the biggest reward. So if rot drink and pass the class gives me a total reward of 15, then that's the best sequence to take over my next couple of days. If I have, I don't know, 3 days. If I have 3 days to study, then my discount factor that I choose, this is not something that the model comes up with. You give the discount factor. Then I care more about short-term rewards than do about long-run rewards. If I rot for 3 days, say I don't have a discount factor. I rot for 3 days, I'll have a reward of 3. Versus if I take this route for 3 days, I'll have a reward of 15. Does that make sense? It's like, even though this will infinitely give me more than taking the r equals 15 route, it depends on what I care about. If I want the reward now, then I'll take a lesser reward that I would get than if I had a year to study. If I had a year to study, I could rot for every day and get a reward of 365. And then like rot, drink, and pass the class at the very end.
Okay, that makes sense. So it's also based on like the time frame that you're dealing with, like how many like times 3 steps that you're doing.
Yeah, like imagine you're playing a video game and there's like a countdown that you need to like make it out of the dungeon in for, and every like you have to like go through like a maze or go through some sort of maze. Then but there's like other special things you can get, like a, I don't know, like a rock, like a special magic rock if you go off to the side and stuff. But if time is of the essence, you're not going to get the special reward because all you want to do is get to the goal, which gives you the biggest reward if you have like 2 minutes. Versus if you have like a maze game and you have 2 hours to do it, then you can collect all the special items and make it to the end in time and you're fine. So it depends on what you care about.
Okay, that makes sense.
Okay, so that's MRPs. Now I'm going to start sharing on this computer. We're going to do a quick coding example, which is sleep, Taco Bell, or the gym. Okay, let me stop sharing. Give me 1 second. I had to shut down my VS Code recently, so let me open things up again. I hope this will load. All right, here we go. Okay, can everyone see?
Yes.
All right, so this is just a very, very simple Markov chain. This is not a coding, this is not something you're going to do in real life because in real life, no one uses a plain Markov chain. Everyone's going to use like some sort of reinforcement learning technique that we'll go over next week. That will be a more interesting coding example than this. This is just basically purely for just visualization. Let's say I have this directed graph. Every day I'll take a nap, I'll go to Taco Bell, or I'll go to the gym. Depends on how I'm feeling, right? If I'm taking a nap, there is a 60% chance that when I wake up, I'll go to the gym. I'm well rested, I'm feeling up to it. But let's say that I am at the gym. If I'm at the gym, there's a 60% chance that tomorrow I'll also gym because I'm like going in the moment, I'm just feeling it. If I eat Taco Bell, I will gym the next day because I Taco Bell. That's like the worst thing ever to eat.
You're gonna make yourself go to the gym after that.
Like I gotta go gym after that. If I'm at the gym,
I think you're dead.
I'm not gonna stay at the gym. My chances are that I'm more likely to go grab some Taco Bell because I'm hungry than I am to go home and nap.
Gotta digest it under the safety of unconsciousness.
I don't know if I
Taco
want to
Bell
put
and
other
gym
people.
straight after, that's a dangerous game.
Yeah, I don't know if I want to subject other people to the disastrous after effects of that Taco
Yeah.
Bell.
You get your Taco Bell protein.
Some extra napkins there.
So this is gonna be our idea of the Markov chain, and these are gonna be our different transitions, and that's gonna be your transition matrix directly based on that. So sleep, sleep, sleep to gym, sleep to Taco Bell, and vice versa. We need to make sure that each row adds up to 1. So that's exactly what we're doing right here. We're adding up each row and make sure it adds up to 3 because we have 3 states. Yay, that worked. And then we're going to create a function that sort of simulates our daily activities. And we call the activity forecast. It's going to tell us what we're going to do every day and tracks the cumulative probability of that exact path. So same thing that, if you guys remember that very ridiculous long recursion problem that we had, this is going to be the same thing, so we're going to use a while loop, like a loop instead. But this is basically just simulating that. So I can choose, where is it? It's gonna save all the activities we do. It's going to go through however many iterations we want, and then based on that entire list, it's going to tell us what's going to happen. So let's say we start with sleeping, and then we want to know what's the probability that I'm tweaking. What's the probability that we're going to end up starting at sleep, ending up at gym, just given that using this function here. So the activity today is going to be sleep, and so already our list is going to have the activity today. And then we're going to start off with our probability equal to 1 because we're going to keep multiplying against it. If you remember, we had that really big sequence that was just multiply, 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 etc., etc. So unlike before when the main thing was that, oh, let's account for every state we can have in between. Instead, what we're going to do is just take a random value of what that in between state will be. That's what this is going to be here. What will our transition be? Are we going to go from sleep to sleep? Are we going to go sleep to gym? What is going to happen? It's just going to be that random probability based on our matrix here. And that's what it's going to say, is that if we're going to be sleeping today, what's the probability that we're going to end up gymming? And all those in-between states are going to be completely random. So let's see what we get here. The probability that we start at sleep and end at gym is 0.6132. Now, if you solved it out, you're going to say that, oh, wait, our gym one is 0.5667, sleep is around 0.2, tackle ball is around 0.2. Comes out to there. This is quite close. That if our ending state is gym, so our steady state probability is gym, this is quite close to it, given that we're randomly simulating what happens in between. So that's pretty much the idea here. It's not really that interesting in my opinion. It's just sort of a way to think about it, another way to look at or remember how steady state probabilities work. That's pretty much it. Next week's coding example will be fun. I can tell you that. It'll be reinforcement learning. Anyone have any questions about the coding example?
No.
Okay. Besides that, I think we're pretty much done then. It's like 7:30 for me. I gotta eat and I've got work tomorrow. Anyone have any questions about Markov chains or anything you guys want to see in the reinforcement learning slides next week?
I can't think of anything off the top of my head. Like suggestions to put in the slide. I'm a little bit new here, so I don't know about giving you suggestions on how to teach.
If you guys have any ideas that you want to see for RL at least for next week, just like put it in the chat in like the workshops Discord by like Friday-ish, and I'll make sure I incorporate that. But I hope you guys learned stuff about Markov chains, and I hope some of the things weren't too scary and complex. As long as you get like the main ideas, it's good.
That's the whole reason these chains exist, is because we're not actually using a DAG all the time. We're just using a directed graph, so we need to be able to account for the cycles.
If you want to know the real reason why it was invented, it was a math competition between like old Russia, between Andrei Markov and another more religious mathematician, and he believed that the law of large numbers could prove that there were independent events, that if you saw it, it meant that events are independent. And so he tried to use it to mathematically prove that free will existed. And Andrei Markov, he didn't like the guy, so he made Markov change to prove that dependent events also followed the law of large numbers, therefore proving that just because you see the law of large numbers, you can't infer that the events are independent.
Interesting. That's a fun
I
story.
did not know that. That is very funny.
Yeah. But
Oh yeah, that's it for me. I hope you guys learned something and I hope you guys had fun.
Thank you.
thank you.
Thank you.
Enjoy Texas.
Yeah, enjoy.
I will try my best to.
Okay, bye.
Bye.